In Chem 1A, you learned all about Lewis structures, the octet rule, bond order, etc. And these rules were generally applied to smaller atoms, like those in the first couple rows of the periodic table. But you probably remember some rule breakers and exceptions, like metals or heavier atoms, which could sometimes have upwards of 12 electrons around them. Frustrating as that was to remember then, it's kind of a neat trick that elements further down the periodic table are able to do that, and crucial to coordination chemistry. Whereas before, in those earlier atoms, we only had s and p orbitals available for electrons to go to. With the larger atoms, like transition metals, the d orbitals are now up for grabs. Recall the 5 different d orbitals: dxy, dxz, dyz, dx squared minus y squared, and dz squared, as drawn here. Now, in a plain lone transition metal atom, all of these d orbitals are degenerate, meaning they're at the same energy level. But things get a little messy when we start adding ligands around that metal. When the metal and ligand bond, they're sharing electrons between them. And remember that even though electrons can pair up with each other in the same orbital, their negative charges repel each other, and they generally like to keep their separate space when they can. So when we introduce these electron-rich ligand-to-metal bonds right where some of these d orbitals are, they get a little too cramped, getting unhappy, raising the energy of that orbital. In this example here, where the 6 ligands form an octahedron around the metal, the orbitals that experience the most overlap are dx squared minus y squared and dz squared. The other 3 d orbitals still see a little overlap, but not quite as much, so their energy goes up less. And the difference between these 2 new energy levels is called the octahedral field splitting, or delta zero, or sorry. A counterexample is the less common tetrahedral complex, like this one drawn here, or ML4. Although it's a little harder to clearly see the overlap between orbitals and bonds, what's seen is the opposite effect. Now, orbitals dxy and dxz and dyz are all at a higher energy level than the other 2 d orbitals. The difference this time is called delta T, or the tetrahedral field splitting, and because the overlap is less defined than that earlier octahedral case, for any given metal-ligand pair, a delta T is going to be smaller than its delta O. This fact is not necessarily important for you in this course, but it's just kind of neat to know. So the greatest factor in dictating how large this energy difference is relies on the ligands involved. Ligands are defined as either strong field or weak field based on where they lie in the spectrochemical series. Anything that's stronger than water, like cyanide, is a strong field ligand, meaning it will widen that delta O energy gap. On the opposite end, ligands like chloride or iodide are weak field ligands that only split the d orbital energies a little bit. Let's look at an example with the strong field ligands, like the octahedral complex COCN6 3-. So I want to know where the electrons are in the d orbitals, and I'll place them there. So to do that, I'll first want to figure out just how many electrons there are in the valence shell. So to start, let's determine the oxidation state or charge of cobalt. The total charge of the complex is -3, and -6 of that comes from the cyanides themselves. That means then that cobalt must contribute a +3 charge. So we're looking at cobalt 3+, which is just like a neutral cobalt, but with 3 less electrons. Looking at our periodic table, we see cobalt is in group 9, so neutral cobalt has 9 electrons, and thus CO3+ has 6 d electrons. Now I just need to start adding my electrons to the orbitals one by one until I need to start pairing them up. But wait, I have a strong field ligand here, cyanide, so putting an electron in those higher energy orbitals is actually going to be pretty tough and more costly than just putting them into the same orbitals below. So for this, we're going to completely fill the lower energy orbitals before getting to the higher energy ones. This is called low spin because the up and down spins of the electrons are able to cancel each other out when they're in pairs. What if instead I had a weak field ligand, like COCl6, 3-. I still have the same number of electrons to place. It's just that now delta naught is a lot smaller because I have a weak field ligand. So I can fill the higher energy orbitals before making pairs. And this is called high spin because now the spins are mostly all up and are able to cancel each other out.